One presentation for the Miele C1 compact vacuum cleaner. The upper shell assembly and the lower shell assembly have been made through injection molding because they produce smooth and uniform surface finishes, parting lines on the seams, complex geometries, various wall thicknesses. Injection molding is great for high production volume and for creating parts of color and complex geometries, as you can see on the left-hand side. Also on the website, they actually do state that all these parts are made in with injection molding in China and Dongguan. An alternative would be thermoforming, vacuum forming, because all it requires is that you put a plastic sheet into a three-dimensional, you can use a plastic sheet to create three-dimensional shapes in a vacuum and pressure chamber. But any holes that you're going to make in the part has to be done in post because it can't be done made in the process.
The smaller parts that are inside the vacuum are also made through injection molding and also extrusion. So the injection molding would be for the circular parts with the more intricate designs, like with the holes, and the extrusion would be for the longer parts, like the circular pole and the pin in the top right picture. And then the filter bag tray, also with injection molding for these more complex designs, again with the holes, and the bending for these long plastic tubes as it needs to work its way around the manufacturing process of the vacuum. And alternative manufacturing processes, we were thinking compression molding for that little divot on the left-hand side, but it would be inefficient. And also with 3D printing, while it is possible, it's very inefficient with mass production.
For the power cord, the copper wire is extruded through multiple sets of dies, and then it is cooled. And then as it is being extruded, a PVC coating also coats it. Next slide. For the PCB power supply, there's two manufacturing processes I'd like to consider: refill soldering and photo etching. Next slide. Alternative manufacturing process would be wave soldering and chemical etching. For wave soldering, it's faster, cost-effective, reliable, but it's not suitable for surface-mounted components. For chemical etching, it's high precision, low temperature, cost-effective, and it produces chemical waste, which is one of the cons. Next slide.
This next section will cover components and pieces associated with the motor assembly, which are the motor case, cover, and impeller. Starting with the motor case, this case is most likely casted steel. Casting is done by pouring molten steel into a mold that meets design specification of the product, which can be assumed manufacturing process based on the seams and gates present on the bottom of the casting. An alternative process would be extrusion, which is another manufacturing process catered towards making these complicated 3D shapes. However, that's not better as casting could achieve higher dimensional tolerances. Next would be the motor cover, which we believe it to be made using stamping, which is press forming flat sheets or coils into specific shapes. With the thin thickness, this makes it a great thin material. It makes it a great candidate. An alternative process would be hydroforming, but the tooling has a higher cost. Finally, the motor impeller, we believe this to be made using rivets, as you can see on the bottom. Rivets are inserted into the holes and peened open. Another alternative could be welding, but it's hard to make with small pieces.